O ya cuando que no vean la...
Hello, everyone. Welcome to ITS 450. Just letting everyone in. All right, so I think that's everyone. Okay, so today we have today's lab, as you know. So I'm going to start there with the lab assignment. Okay, so before I begin, are there any questions? As you know, both labs are due tonight, the set UID lab and the format string vulnerability lab. Both of those are due tonight by 10 p.m., I believe. So make sure you submit those labs.
Professor Calix, I'm sorry.
Yeah, go ahead, please.
Hey, is there any way we could get an extension for that second lab?
Extension. So are you guys done? So, okay. So yes, but my concern is, what are the problems? So for the set UID lab, that's okay, right? You guys have done that?
I've done that one.
Okay. All right. So then just for the format string, you want an extension.
Please.
Anyone else need an extension on that one?
Yes.
Yes, please.
Okay. All right. So sure. So actually then let's start there. Instead of me introducing third lab, which is buffer overflow, which is considerably more difficult, I can give you the extension, and then actually I'll do that now so I don't forget. And then just please ask the questions that you might have. All right, so format string. I'm going to share my screen so you can see what I'm doing. Okay, format strings, you should be seeing it now on Brightspace. Okay, so here it is. So the due date, today is the 10th, and the due date was today, but now I'm going to extend it to the 17th, the 18th, okay? So that should take care of it, I think.
Thank you so much.
Maybe double check on your end that I did modify it. Brightspace, I'm still getting used to this. Okay, update. All right, so now it should show. Did you guys check to see if it modified? Oh. All right, so then 17th. Okay, that should modify it. All right, so it'll close on the 18th next Friday, but it's due on Thursday, this September the 17th. All right, So what questions do you have on format string? What are your questions? No questions? Okay. Have any of you submitted the format string lab at this time?
I have.
You
Yeah, I
have.
have two.
Okay, great. So some of you have submitted. So I guess if questions come up for format string, just let me know. Otherwise, then we should be ready. Some of you, I guess, have finished and are ready to work on the next lab. So let's go in that direction. Okay, so I want to go to table of contents. And then as you know, we've got set UID, format string, and then we have the buffer overflow lab, right? And then this would be technically the last lab before you do your practical exam. So remember, your practical exam will be in about 2 weeks, and it'll include these 3 labs. And as I said, it's just one problem where you have to do a code injection. So basically, I explained a lot of things in the lecture on Tuesday. I haven't finished with that, so we're going to continue with it. But that's the general idea. So we can go ahead and download the buffer overflow document. And now we can go to downloads. Okay. Okay. So I posted one version of it. Yep, here it is. So can you guys, oh, you're not seeing it, are you? Okay. Okay, so you should be seeing it now, correct? The PDF?
Yep.
Okay, great. So the buffer overflow vulnerability lab. Okay, so this is the one we're going to work through. As I said, we don't always have to do every problem in these labs. I will usually just say in the drop down, or sorry, in the link, which parts of it I want you to focus on. Okay, so the learning objective of this lab is for students to gain the first-hand experience on buffer overflow vulnerabilities by putting what they have learned about the vulnerability from class into action. Okay, buffer overflow is defined as the condition in which a program attempts to write data beyond the boundaries of pre-allocated fixed-length buffers. Okay, and that's kind of what I've been discussing in the lectures, right? And I'll continue to discuss that until we're done with it. So as I told you, this lab takes 20 minutes to do if you know everything that you need to do, but it takes a lot of imagination, if you wanna say that, right? It takes a lot of like you thinking about the code and how it's laid out in memory and all that, so for it to make sense. So this vulnerability can be used by malicious users to alter the flow control of the program, leading to the execution of malicious code. So this is literally the most dangerous thing, and it's the problem that has been plaguing Windows and operating systems since they were invented, basically, right? So this has been, whenever you think of exploits, whenever you thought about, oh, why we need to patch all that, it's because of this, right? So as I've said many times, C++ is an exceptional language that has been around since the 50s, 60s, and still the most important language basically. And so but it gives you a lot of power at the low level, at the hardware level, you know, very close access to memory. And so it's important that we understand, you know, why, you know, what the principles, basically, the basic ideas of this. So far you've done the set UID, which allowed you to understand how to get the root privilege. And then we talked about a process and how spawning, you can spawn a process from another process through the system call, a specific type of system call. And we looked at in the format string lab at playing in memory, playing with the memory, right? So now these ideas are just going to be extended to, you know, more complex, but they're basically the same thing. It's just, it's going to be a little bit more complex now. So as I was explaining, this is a lab. Sometimes, usually we have a lab and it doesn't require that much discussion. This one really does. So that's what I'm going to do today, really. Just, you know, lay out the basic ideas. So stop me at any time if you have any questions, and so on. So as I said, this vulnerability can be used by a malicious user to alter the flow control of the program, leading to the execution of malicious code. In this lab, students will be given a program, right, with a buffer overflow vulnerability. So that's why on Tuesday I spent so much time, you know, writing code, C code, and showing you, okay, you know, this happens, that's a problem. So the basic idea is that you're going to have a vulnerable program, okay? And their task is to develop a scheme to exploit that vulnerability and finally gain the root privilege. In addition to the attacks, students will be guided to walk through several protection schemes that have been implemented in the operating system to counter against buffer overflow attacks. So students will need to evaluate whether the schemes work or not and explain why. All right, and as you can see, the lab will cover the basic idea of buffer overflow vulnerability and attack, which is what we've been discussing. The stack layout in a function invocation, which again is what we've been discussing in the class. We're going to talk about shellcode, and I've been mentioning this quite a bit. So shellcode is basically a C program that when you run it, it just triggers a shell. So usually one thing that I suggest you do in this lab is just at the very beginning, you're going to see here's a little shellcode program. You know, download it or write it on your write the code, compile it, run it, and you will see that when you run the program, it'll create a shell. What I mean by a shell is it'll give you a terminal. It's literally like it's calling bash or dash. And so you can see that you can run it, and that's the first thing because you'll have the binary of it, the executable, and then from there you can think of, okay, now I'm going to, you know, that code is machine code or is a binary, but now how do I convert it into the way that this program would be represented in memory somewhere, right, in memory. So it's really about, remember, it's all about the CPU. The CPU is trying to execute a sequence of commands, and so you want to give it the instructions perfectly without encountering any errors. Okay, after that, after the shell code, you're going to then look at some of the controls that are in place, such as address randomization. So as you probably have seen from the discussions, the lectures, you know, there's always addresses involved, right? So there's an address here, an address there. So address randomization, non-executable stack guard. So there's a few controls in place to prevent this from happening, right? So we will get to those. Okay. Right, and then return to libc as it's stated here. This principle, which aims at defeating the non-executable stack countermeasure, is covered in another seed lab, so that will not be covered here. So which is, yeah, so don't worry about that. We will, I will provide what you need for that. So as you know, this is chapter 4 of your books, the Seed Labs. So, you know, follow along with the reading there. Okay. And then there's some video that you can take a look at there as well. All right, the lab environment is 1604. Okay, so the same VM that we've been using so far, so that's great. Now, so for this lab to work, the first thing you will do is you need to turn off some of the mechanisms, okay, some of the security mechanisms. So one of the first countermeasures is that you randomize the address space. So in a sense, the idea is that imagine that you have a big table, right, where every cell is a different address in memory. And so the idea would be that the stack is sometimes created on the upper left hand without randomization, the stack is always created in the same place. Let's say the middle of the table, always. But with address randomization, what would happen is sometimes the stack is started in the upper left-hand corner, sometimes in the upper right-hand corner, sometimes in the lower left-hand corner, and so on. And so you're varying the addresses. So knowing the address beforehand, it's not going to help you because it's randomized, right? It's randomized. So even if because one of the things you have to do in this lab is you have to figure out what the return address is. And we talked about that last Tuesday. And so what you have to do in this one then is figure out that address first, right? And that's why we turn off address randomization. We turn it off so that it makes it, every time you run the applications in the OS, it's always the same place where everything is laid out on the stack, and it allows you to find it. Later on, we're going to see, okay, well, if you turn on address randomization, does that mean that you can't do this anymore? Well, you'll see the result, and you'll see that actually the address, there's one important principle, and that is that even though it seems like there's a lot of addresses, actually an infinite number of addresses would be pretty big, but a computer has a very small, actually, I mean, in terms of computers, very small space for addresses. So the range is actually quite short. So basically a type of a dictionary attack works really well. Just try a lot of addresses. Eventually you might succeed. All right, so we will see that later. So to turn off the countermeasure, so you can execute the lab task using the VM, Ubuntu VM. You will need to turn off these countermeasures. So for the address space randomization that I was just explaining, you will follow these instructions here, right? So Ubuntu and several other Linux-based systems use address space randomization to randomize the starting address of heap and stack. This makes guessing the exact addresses difficult. Guessing addresses is one of the critical steps of the buffer overflow attack. So to disable it, you'll just do this. Kernel randomization. Another countermeasure is what is called the stack guard protection scheme. And that's related to the GCC compiler. So whenever you grab the code and you compile it from the C code to the executable, you always can specify a flag, as you can see here, right? So that's, however you would have written your GCC program, however you would have written it, you just have to add now this parameter in there. And what that does is it sort of disables that stack guard protection scheme. So the stack guard, the GCC compiler implements a security mechanism called stack guard to prevent buffer overflows. In the presence of this protection, buffer overflow attacks will not work. But you can disable it while compiling by using this flag on there. Okay. Non-executable stack, I believe this is already disabled in the Ubuntu and the CVM. So let's see, Ubuntu used to allow executable stacks, but this has now changed. The binary images of programs and shared libraries must declare whether they require executable stacks or not. They need to mark a field in the program header. Kernel or dynamic linkers uses this marking to decide whether to make the stack of this running program executable or not. Okay. I guess to change that, use the following option when compiling programs. So you will also then try this. Okay. And then configuring bin.sh. Let's see this. In both Ubuntu 16.04, the sh is, okay, you already know this. You learned this from the previous lab, right? That sh is a symbolic link to dash. The dash shell in Ubuntu 16.04 has a countermeasure that prevents itself from being executed in a set UID process. That's right. Basically, if dash detects that it is executed in a set UID process, it immediately changes the effective user ID to the process real user ID. See, this is something I had talked about, essentially dropping the privileges. The dash program in Ubuntu 12.04 does not have, well, you're not using 12.04, so. Right, so initially then, you're going to have to not use dash is what this is saying. So therefore we will link bin.sh to another shell such as CSH that does not have such a countermeasure. So this was the question I think that Austin had asked last week, right? You remember that he was only successful when using not dash. So basically that same idea applies here, although we will later look at how to get around even that mechanism. Yeah, so therefore we will link bin.sh to another shell that does not have such a countermeasure. In later tasks, we will show that with a little bit more effort, the countermeasure in bin dash can easily be defeated. And of course, you have CSH as the program that you can use that has the vulnerability. And that's why, you know, as I said, now that you've done the set UID lab, this should be pretty straightforward. And then this is the same command for breaking the links, right? So you know that. All right. So are there any questions so far?
No questions.
No questions. Everyone's, oh, great. Excellent. I'm glad. So now the very first task is just pretty straightforward. You can see this has a little bit more code, so you're going to have to copy this into your own Ubuntu. But the first thing is really running shellcode, okay? Running shellcode. So what that, then this is something I said initially as I was talking. Shellcode is, you run this program and it gives you a terminal. You can see that here, right? If you look at this program that I'm highlighting right now, you know, it basically calls the name, the main, it's got a variable there, like, and then it assigns to it bin.sh. And so it's really like a string, and bin.sh, as you know, is what you would type on the terminal to call a shell. And then when you run this exec v, you're really doing like a system call, and then it calls bin.sh, and boom, you get a terminal. So that's really what I want you guys to do first. You know, what this lab wants you to do first is just to take this program, compile it, run it, convince yourself this little piece of code here, will give you a terminal. Why is that relevant? Well, it's relevant because in this attack, you're going to do a code injection. And what is the thing that you're going to be injecting? So what do you think is the thing that you'll be injecting into this vulnerable program as it's running? What's the code injection?
Are we just injecting that code right there?
Yes, we are just injecting this code right here. Exactly, very good. So if you remember, as we were talking you know, last week, for instance, you guys were you know, trying to inject a number, right? Using percentage n, you inject it like a number, and then you change something in memory. This time around, we're doing something more complex, but it's the same idea. We need to find a way to inject this into memory. We need to figure out where we placed it in memory by knowing its address. And then we need to go to that other place that I described on Tuesday where the return address was, and we're going to put that address there. And once we do that, the CPU will eventually look at that return address, read it, jump to the place where that address is, which is the place where this code is stored, and run this. And guess what? When you run that, the CPU will run this independently, exactly like it is from beginning to end, and it will give you a shell. And then finally, once you have that shell, you will want that shell to be a root shell. Because once you have that root shell, you can basically do anything on that computer. Does that make sense, guys? That's literally the objective of this lab assignment. That's literally it. It all revolves around this. It's simple, a simple idea. It's just the details are not as simple. But all we have to do is inject this. Now, we cannot inject the code as is, right? This code will not actually, if we inject that, the CPU will not know how to interpret that. So what we need is we need to take the machine code version of this. So after the compiler grabs it and does its thing and it converts it into machine code and opcodes, that's really what we would need, okay? So, but the first thing you should do though for this lab is just grab this code, compile it, run it, and generate a shell, terminal, kind of the prompt where you can type commands, and that's what's called shellcode. So let's look at task 1 then. So before starting the attack, let us get familiar with the shellcode. A shellcode is the code to launch a shell. It has to be loaded into the memory so that we can force the vulnerable program to jump to it. Consider the following program, okay? And so now I will show you guys, I will describe in more detail how we're going to achieve these goals, okay? If you were trying to, so you might imagine then, if you were trying to inject, say, another program, you'd have to do the same thing. You'd get that program in its C version, compile it, convert it into the machine code, and then that machine code would get injected into a place in memory. Again, then find out, figure out where you put it in memory, grab that address, and put it in the return address. Okay, so that is what this lab is all about. That's what the practical exam will be about, literally. You'll have, again, same idea. And so, and that's it. All right. So the shellcode that we use is just the assembly version of the above program, right? So the following program, the one that you see down here, is actually now, it actually now has the shellcode. So conveniently for us, we don't have to, go and take this and produce the shellcode. It is given to us, okay? So the shellcode that we use is just the assembly version of the above, and the following shows how to launch a shell by executing shellcode stored in a buffer. So you should also run this program. So please compile and run the following code and see whether the shell is invoked. You can download the program from the website. Right, and you can see that here. So we have call shellcode. And now this part here, this there is exactly the shellcode. Okay, so you could say it's almost like this one, except, so the process is you take this and then you follow the process and you get something like this, but usually sometimes you have to make slight modifications because there's basically a couple of ways of doing things, and sometimes one way is a little bit better than the other. The other one might include an error here and there, and you obviously don't want to. So let's just say that this shellcode is an optimized version of the original shellcode that you would get. Okay, and that's why we don't really need to get into that. We just need to understand that from this, after you compile and you get to the machine level code, you get something that looks like this. Okay? And so now this program treats this code here as a string, basically. You can think of it as a string. And then down here, it's going to take that from code and copy it into buffer, right? And then it's going to try to run buffer. And then once it runs buffer, it points to that, the CPU hopefully will generate a terminal for you, okay? So that's the idea. Are there any questions about this? So initially, this task 1 is all about the code that you're injecting, okay? Which is ultimately that one. One thing that's going to happen at some point in the lab is that you will succeed in injecting this code into memory. When you do that, I strongly suggest that you view it. Try to view it and try to find it. It's always very satisfying to figure out, oh, I found, remember that these things in the stack get inverted. So you might find like x80, then followed by xcd, then xob, bo, x99, and so on. And so once you find this in memory, you'll know, okay, you succeeded in adding it into memory. Now you need to figure out with that mechanism, what's the address space and everything for the second part. Okay? All right, so that's your task 1, right? Task 1, compile this one, compile the other one, run them. You need to get a terminal just by running them. No code injection, no anything. Just prove to yourself that you can do that part. Okay. So I'm not hearing any questions. So then I'm just going to continue. So here's the instructions on how you could do that. Compile the code. Compile the code above using the following GCC command, run the program, and describe your observations. And please don't forget to use the exec stack option, which allows the code to be executed from the stack. Without this option, the program will fail. Right? So just disable the executable, those controls for executable stack. Okay. Now, as I said, the shellcode above invokes the execv system call to execute bin.sh. A few places in this shellcode are worth mentioning. Now, this is really outside of the scope of what I think we should cover, but just want to mention that this is the part that you see here. If you can see my mouse, that's like the opcodes, the machine code. This part here is assembly. So it's the assembler version of your original C code. You can see it's got commands like push, move, in. So usually when you see those XOR, L, those are basic assembly commands. And then usually over here you have what's in the registers, right? Or you have some addresses or things like that. Okay, and so it's, if you want to understand a little bit more about assembly, or you want to understand a little bit more about shellcode and some of those issues, you can read through this. You don't need this. You don't really need to understand this paragraph to do the lab, but it's useful if you wanted to take it a step further, right? So you want to optimize your shellcode even more. All right, so now the vulnerable program, right? So who can tell me, based on what we've been discussing in this class this semester, right? What creates a vulnerability in a program like this one? What's the vulnerability?
printful function
A what?
without the printful function without the reference in the stock.
Yeah, the printf function, right? That's what we saw in format string. But what about, so what we were discussing this Tuesday, for instance, about buffer overflow vulnerability. Try to remember that. What was one of the main issues that I mentioned there?
Would it be a way to import or to input a string larger than the buffer?
Yes, exactly. That's exactly what it is. So as you can see here, this is your vulnerable program, right? This is what you will use. It has a buffer overflow vulnerability, okay? Where you see the line 1, there's a problem there. Your job is to exploit this vulnerability and gain the root privilege. As you can see here, the buffer size is defined of a specific size, let's say 12, 24. You know, you can try different values. You can see the suggestion there between 0 and 400. But it's important that it be limited. Okay, you can play with that because playing with that, remember, it's like an offset. So you're figuring out where the return address is in the stack. If you remember, we discussed that on Tuesday and I gave you the layout of that. So you kind of want to figure out how big you want that to be. All right, so you can see here that we have the main. Notice that this continues down here, right? But we got the main in there. And this actually reads from a file. It creates a file, bad file, okay? So that file will have, you know, let's just keep it simple for now. Let's just say there's a lot of data in that file right now, right? In fact, there's data of size 517. But then that data gets read into this variable str, and then that str becomes the input to the function buff, BOF. And that's where the problem is, because first of all, buff is now a function, right? That means that this function is going to be placed where in memory? What's the name of the place where, when you have a function, where do you put its variables?
The stack?
The stack, exactly, the stack. Notice this has one argument string and it's got local variables, okay? So now in the stack, you're going to have something that is of size 517, right? You're gonna have something pretty big and you're going to try to write that into buffer. And buffer, notice right now, is of size 24. And then this is the problem, that you're using this function string copy, which doesn't check the bounds. And it literally will just try to copy something that is of size 517 into something that is of size buffer. Does that make sense, guys? Okay. And so that's the problem, right? That we are going, that's the code injection is whatever you have in this string. And that's one of the challenges in this lab. You will have to basically construct that code injection. You need to figure out where it starts. The first 24 bytes here don't really matter because that's buff size, but it really matters that you need to figure out after those 24 where the return address is. So put that there. And then you still need to figure out how you're going to jump, and so let's say that you know that you have the address of your code, but then you still need to figure out how you're going to put your code in memory. So this is something that I know I haven't mentioned yet. I remember I didn't say this on Tuesday, so that's what I'm going to explain now. Okay, so I'm going to switch over to the whiteboard. Are you guys seeing the whiteboard?
You see it?
Yes.
All right. So what did we say about the stack on Tuesday. We said that it had some variables over here. And then here you had like the return address. Right? And then you had more more things, metadata. And we said that this is the frame for the current function, let's say buff, right? So now we got a name for the function buff. So let's say that you figure out, you know that that variable, what was it, buffer? Buffer? But it's of size 0 to, let's say, 24. Okay, something like that. But you're writing in something that is of size 517, much bigger, right? So it's going to overwrite this. This is the thing that you want to figure out, you know, the size of this, where does it start, right? And so when you need to create the code injection, these 517, you need to create it. It's going to be nothing more than a string of characters. So it's possible that the first 24 don't matter. But then you have to figure out this metadata. You know, what size is that? And then you've got your return address. And here, that's still probably less than 40 bytes. And it goes all the way to 517. So you sure have a lot of room in there. It's like a very long train, and most of it is empty, right? So let's say that you figure out, so again, you just need to create a string that looks like this, right? Most of this doesn't matter. This part really does matter. Okay, getting that correct, the return address there. And return addresses look like this. You know, BF, FF, 43, D, B or something. So they're really just about 8 characters with the hex in front. That's about it. So you'll need to figure that out. Now, let's say that you figured all that out. Where do you think, where could you put the code itself? So that's shellcode that we talked about, right? So we've determined that the CPU, we want it to eventually read the return address. And then from that return address, jump to the shellcode. You also know what the shellcode will look like because I just showed it to you, right? I just showed it to you. So we know that. So the only problem is now we got this return address here, and that's going to be pointing to the shellcode. So where in memory do you think you could put the shellcode? That's really like one of the main questions left to answer. Where could you put it? What do you guys think? Any ideas?
Is it by any chance supposed to be in the return address?
The return it can't be, the shellcode cannot be, do you mean here in the place of a return?
Yes.
It can't be. It's not, first of all, it wouldn't fit.
Okay.
Second, the CPU is looking there for an address.
Okay.
It's not going to, I see what you're saying, but the CPU, imagine the CPU is like a person, right? And all they know how to do is they need to look at that, and based on what they see there, then they jump somewhere. So it's almost like it has, you want to think of it that way, it's almost like the CPU has this function. It's going to invoke this function called jump, but it needs to provide the value in there. And then when it jumps to that, it's going to execute that. That's the sequence. So what do you guys think?
Okay, so then it'll go to that particular address where it's going to jump to then?
That's right. The CPU will look in here. Whatever's in there, it'll jump to that specific place in memory and it'll start executing the commands there. The shell, you know, you want it to execute the shell code, but usually it would be the return address to the program that called the function. So initially, so let me share. It should have been, so the correct thing would be, just like we did in class, right? The return address would be, let's say, let me just put it this way. Of these 5 statements, right? Assuming buff is the function in question, the frame that we're looking at in the stack, which one of those 5 should be, which one of those statements should have the return address? Or let me put it in another way. Which one of those 5 would be the one that the return address is pointing to? So when the CPU reads the return address, it'll jump to one of those 5 that I highlighted. Which one of those is it?
Return 1.
Which one?
Return 1.
Not return 1. You're close. But remember, what is BOF here? BOF is a function call, right? And if we scroll up, we just saw it's this one, right?
Yes.
So in just with this idea of this is what we have in memory currently at the frame, right? Then once this function finishes executing, what's the next instruction that it should execute? Once the function buff finishes, what's the next instruction?
Printful.
Yeah, printf, right? Printf return properly, exactly. That's the next instruction. So given that logic, go back to what we were looking at. Given that logic, then the return address here should be for that printf. Does it make sense now?
Yes.
Okay, so then jump would grab the address, jump there, do printf. That's how it should execute. That's what the CPU should do. But because you're trying to break things, you want to overwrite that. And you want to put in here your own address. You're going to say, no, I have another address, 0xBF FF43BD. You see that? That's your first goal. To successfully put the address that you want in. However, which address? Well, it's the address. If the CPU wants an address for some code to jump to, then you need to also provide an address where once it gets there, it executes code. Which code it should execute? This code, the shell code, that one. Notice that what you see here is, this is comments, right? Notice that those are comments. It's really this one, the 0x31, XC0, that's the one that is being executed, okay? So that's the code that you want it to run. So now I ask you the question again. Okay, we already understand that we put an address in the stack, but which address? Because we need to put that shell code somewhere in memory, right? So So any ideas?
Can we do it right after the return address? So then, and like, because like that's the string where the code is stored. So you put the code, you put the shell code in the string after where your return address would be, and then have it returned to right after.
Well,
So then it would just continue where the buffer was.
let's think about what you're saying. So you're saying, you know, somewhere here, let's say, still plenty of room, put the shell code. And so now when you insert, when you do that code injection of 517 and you overwrite the buffer in that direction, and let's imagine that all of this is the overwrite, right? Not only are you putting the address, but over here somewhere, you put the shell code. So does it meet the requirements that we need? Well, the shell code would be there. The opcodes would be in memory. This is an address space. All of this is an address space. So therefore now, what do you need? You need that address, right? So imagine that that address is 0xBFFF 70 AB, right? Let's imagine that's what it is. So then, based on what you're saying in theory, FF 70 AB. So now when the CPU sees this, when the CPU sees this, it's going to look at that and then boom. And now it's going to start executing all that shell code, and if successful, you get a terminal. If really successful, you get a root terminal. So yes, so she's right. And so now the idea is that you have pretty much defined your code injection completely. You know, it doesn't really matter what you have here. You just have to make sure you know where the return address is or should go. This wouldn't matter, this wouldn't matter, and then just put the shell code there. And then now just know in the stack what that corresponding address will be. So as you can see now that the trick becomes you need to create that input. And that's really what you're going to do in this lab and what you're going to do in your practical exam. In your practical exam, I'm actually going to have you create the injection on the terminal itself. Here, it's going to be a little bit more complex, but that's the idea. That's your code injection right there. Are there any questions? Was this clear for everyone? No questions, really? Making sense?
Yeah.
All right, well, all right, great. So now, so you should be seeing the PDF now. That's what I've switched to. Okay, so now that I've described all of that, we just need to create an efficient way of crafting that string, okay? So it's literally like that. So we have then, just to recap, we have the shell code here. That's the code that we want to run a terminal. We have it here converted to shell code already. You can just use this as is without any modification. Disregard the assembly. That's only there to show you the correspondence of what it would look like in assembly. You run this and you get a shell. Make sure you compile it with this so that you enable the executive stack control. Then we have the vulnerable program, which is the program that literally will take an input. So it'll take a user supplied input. Now that could be, just like we did in the format string, typing it on the terminal. The problem is this one is really big. So 517 characters. That would make the lab a lot more difficult to craft it like that. So the input can also come from a file. Okay, and that will be the approach that we will take. Notice that this program, straightforward, has a variable of size 517. You read the file. You can see that we have an f read there after we open the file. And we copy the contents of that file into string. That ends up being of size 517. And then you call buff, which is the function, and you plug in there the variable string. So you're passing as an argument 517. You pass that here. But the problem is in the buff function, in buff, oops, there, your variable is only of size 24. So that's why it's called a buffer overflow, because the string copy does not check bounds. It just copies whatever is in string until it hits the null character, the end. And so it's just going to keep copying whatever's in here. It's going to have a pointer to where this is, and it's just going to keep writing and writing and writing and writing, and it's going to continue writing in the stack. And so if you align things carefully, you will be able to overwrite the return address with whatever you want and actually put the code, as someone mentioned, put the code in the stack itself somewhere a little bit later, and then you can do the math and figure out where you put it. And we're going to see that there's even other techniques that are going to make this even easier to do. Okay? So the above program has a buffer overflow vulnerability. It first reads an input from a file called bad file. Obviously, we need to generate that bad file, and that will be the thing where you define the entire code injection. It then passes this input to another buffer in the function buff, and the original input can have a maximum length of 517 bytes. But the buffer in buff is only buff size 512. Oh, sorry, yeah, 24, which is much less than 517. Because string copy does not check boundaries, buffer overflow will occur. Since this program is a root-owned program, so that's the other thing, you'll have to make that vulnerable program set UID. So that, you know, what you understood in the set UID lab in 450, now you're going to use it here. Remember, so something is set UID, it means it's going to probably root own, and then you're running it with the privileges of root. Remember that to get the root shell, you will need, initially at least, to use the CSH shell instead of dash to kind of bypass dash's countermeasure. So there's a lot of moving parts. I know it's a lot of, it brings a lot of the previous labs, but it is pretty interesting. If a normal user can exploit the buffer overflow vulnerability, the user might be able to get the root privilege, which is really the goal. That's why when you do this, I will be checking once again, okay, they ran it as seed, they ran the vulnerable program, and now they got a shell, and guess what? The shell is a root shell, so they were successful. And that's the same thing that I will be looking for in the practical exam. So for convenience, the input comes from bat file, but it is user supplied, so it's under the control of the user. So our objective now is what's left is that we need to create the contents of bat file. Okay, and so that's the next part that we're going to talk about now is creating bat file. Okay. Are there any questions so far? All right, no questions. So now what do we need to do as far as compiling? The same idea. You can see here if we do 4755, that's we're making it set UID. You need to think about, make it root own. You can see that there. ch own is root. And then we compile the program and we remove, the stack protection and that, all that stuff. So run it like this. Okay. You can read through this chapter, but I've set this a couple of times. So. And you can try it any value that you want. So just get the basic idea. All right, so now here's the trick. Exploiting the vulnerability. All right, so you need to write now, the input, right? The code injection. That's the next exciting part. And that's going to be accomplished through this. Okay, so let's go back to the whiteboard. Oops, that's pretty busy. All right, so now in that we need to create bat file. Right, we need to create bat file. Bat file is just going to be, let's say, a buffer of size 517. Okay, so initially, you could say, well, I'm just going to mem set it, or like initialize it by default to all zeros. Think of it that way, right? So you can 0, 0, 0, 0, 0, 0, like that. So you mem set, you do that by default. Then after that, let's imagine that alongside here is the stack. Okay, so for the current frame that you're looking at, buff, the address would be there. Right, so let's just say return address. And so that means that the variable buffer starts here. And so you're going to write this input in that direction. So just make sure, it doesn't really matter what's in here, really. But what matters is that this should be aligned. And in there, you need to put the address in question that you want. Okay? That's the address. Then as someone said, but which address? Well, just use an address from this space, right? So these are, I'm just gonna do like 0x40, 0x50, just kind of to make it clear. The addresses are not actually like this. And so on, right? So then, if you put shellcode here, if you put the shellcode here, then basically you just have to align it with whatever this address is. Let's say this one is 0x59, right? Let's just say that's the one. And so basically what that would mean is that over here, 0x59, because you're going to be inserting this into the memory, this code. And so you just need to know, okay, the return address is 0x59. Well, that's this one, right? And then in here, then that shell code will be placed. All right, so this is your input. The code, as it's called, the code injection, this is memory. You just have to create this string. So now you have to piece together, you know, this string in bat file, sequence of characters of size 517. But what's really important is that you get this right. And you get that right. Okay? Are there any questions about that? Okay, so how do we do that? So that's the question, right? So that's the remaining part. You know, how do we do that? And for that, then we can go back to the PDF. So now you will create another program. In this case, it's called exploit.c. This program does not need to be set UID. All it does is when you run it, it creates bat file. And then bat file is the vulnerable program that will read bat file, all 517 bytes, into buff and do a buffer overflow. So this is a partially completed exploit code called exploit.c. The goal of this code is to construct the contents of bat file. In this code, the shell code is given to you conveniently, so you just have to write the rest. So you can see here, there's the shell code. There's the buffer, 517, that you're going to be writing data into. And then then we open file, bat file, right? You can ignore this for now. So ignore that for now. And let's just focus on the last 3 lines. So you can see there, we open bat file with the purpose of writing. See that there, just like in Python, right? And then once we create that file, we copy the contents of bat file. Oh, sorry, we copy the contents of buffer, all 517 characters, into bat file. And that's it. We close bat file. So first, obviously, you will have to write the code for exploit. Then you run exploit. Once you run it, there's going to be a file called bat file in your file directory. Then that file, you should check the size of it. It's going to be 517. And then once you have that file there in memory of size 517, you run the other program, vulnerable. Vulnerable will read that file, read the contents of it, try to write it into buffer of size 24, and boom, you get a buffer overflow happen, exploit. Okay, so now that I've said this, now we need to focus on this part, the one I said disregard for now. So this is the part that's still a little bit incomplete. Remember I said initialize the buffer, and you saw me initialize it to all zeros. So I said use memset, take buffer, and initialize it all to zeros. However, if you look over here, this is actually being initialized to 0x90. And that is called a NOP instruction. So does anyone know what that means, what 0x90 means, or what is a NOP instruction? Anyone know? Who can tell me?
Doesn't it stand for no operation?
Yes, and what is it?
It just tells CPU to move on to the next operation.
Exactly, exactly, very good. So think of this, right? Think of this idea. So we are telling the CPU to look at that place first. That's what it's going to do. And then it turns out that place is 59 here, right? And it contains that shellcode is in there, right? So what the CPU will do is, if you remember the shellcode, and let's actually, you guys can look at it. You look at here. It's too bad I have to flip around so much, but here, let's say 0x31 or x31 xc0, right? So let's try to remember that. x31 xc0. So it's x31 xc0, right? And so on. That's the shellcode. So those commands are there. What's going to happen is the CPU, and I'll just draw the CPU, actually the CPU on this side. The CPU reads 6x31. It knows what it is. Then it reads xc0. It knows what it is and starts executing those things. It does operations with its registers. It looks for things in memory. So it's gonna execute whatever that is. So you can see that the CPU basically has the power to read something there and execute it. So if it has that power, that means it could read something here and execute it, read something there and execute it, read something there and execute it, and so on. Do you see that? So why instead of initializing to all zeros, why are we now saying, you know what? Let's initialize it to NOPs. It's 0x90, 0x90. Just gonna write 90 to shorten it. So why is that relevant? Because before it was a little bit harder, right? We had to know that this was 0x59 to hit right there. If we hit 58 and this is gibberish, it'll break. If we hit just off of 59, let's say 62, it will work. It has to be a precise place. However, the no-op, 0x90, or also known as the NOPs or no-op, increases our probability of success. Why does it increase our probability of success now? Because if we don't get that 0x59 right, it's okay as long as we're close. So now we can just provide, let's say, I'm going to say, well, it's somewhere in this general range. So I'm going to say, I'm going to put here 0x48. What happens there? The CPU reads that information, and I really should be writing down here. Down here, right? So this is 0x59, but in here, in the return address, we actually have 0x42. So when the CPU looks at this address, oh, it jumps there. See that? It really wanted to go here. However, because we have no-ops, by definition, no-ops have a specific behavior. And this, again, goes back to why we did the format string lab. What happened when you did in the format string lab? What would happen when you did this? Who can tell me?
Program crash.
It crashed, yes, but something else was happening.
Overwriting.
We were reading, but something else was happening too. What was happening to the pointer in the stack?
It was moving.
It was moving. Exactly. Very good. It was moving in the stack, right? And here is the same thing. The CPU reads this 90. No op means literally nothing to do except move. So the CPU moves to the next. And guess what that is? It's a no op, right? So what does the CPU do? Nothing, but it moves again. And guess what? It finds another no op. And then what does it do?
Moves again.
Moves again, right? And then again, finds another, and then boom. Guess what? It hits 0x59. And then what happens? It runs the, what is this called? Shellcode.
Shellcode.
That's the shellcode. And remember that that's the little thing that will generate your little terminal. Do you understand, guys? See how all labs are coming together? This is called, it has a funny, I had a student who sent me, you can probably find this on Amazon. He sent me a link to, there's apparently a children's book, a children's book about cybersecurity. And there's one very funny one about the NOP sled. It's got something called the NOP sled. And so really this is called a NOP sled because it's like, as you might imagine, it's a sled, right? You're sliding. When you it's like almost like this, you know, like those in the playground, right? In playgrounds, have that, and then you know you hit there, but you know, and you come down to, and then you hit the end. And so you could say that the shell code is there. You can jump there. You can jump. Oops. You can jump here. You can jump there. Any one of those places, you're going to end up in the shell code. And that's why you have these percentage 90s in there as initial. So when you initialize this entire string, the very first thing you want to do, so if I move it over here now, like that, you know, you're building your 517 buffer for bat file. First thing you do is memset with no ops. Right? And then initialize everything with no ops. You know that you just need an address in the stack somewhere around there. So find this address, which is not trivial. You might want to use GDB. Get a feel for that. And then also, once you find the address, you need to figure out where, excuse me, where on here do you plug it. So if this address is 0x90, oh, sorry, not 0. Long day. If it's 0xBF40, let's say, then what you write here, 0x BFF 40. Like that. And that's it. And then all that's left is that once you figure out where that would be, just figure out the target address. As long as it hits a no-op, it'll slide down to your, what is this again? What goes here?
Shellcode.
Shellcode. Perfect. You are paying attention. That's it. This is literally the lab, guys. Okay, so the lab is so completing this task is the hardest. After there's a few questions after that, but those questions are really easier because you figured out the main challenge of the lab. So now let me switch back to the PDF. And you can see that there. So you can see here that you have the mem set already, initialize buffer with 0x90 no-op instruction, and you have there, basically, these are the no-ops. So you're just initializing it. And then after that, you just need to write the code here. Maybe a couple of for loops would be the easiest thing, where you copy the contents of this shellcode into buffer. Okay, and also the address. So that's not, that shouldn't be hard. I mean, if it is hard, I'll help you with that part. That's not really, you're not learning how to write C code. So you know, that's just, if you've taken a C course and you know it, you know, you can do it easily. So, but the challenge is getting that address and knowing where to put it, aligning it correctly, okay? So work on this on your own, ask questions. I'll help you with this part. That's not, but I will not give you the return address. That's one thing that, also don't give the return address to your friends, right? You know, because remember, you got to figure it out how to do that, because on the exam, on the practical exam after this lab, you have to figure it out in real time, okay? And so that's the problem. All right, so that's the exploit function. As I said, pretty straightforward as well. So after you finish the above program, compile and run it. This will generate the contents for that file. Then you will run the stack program, which is really the vulnerable one. If your exploit is implemented correctly, you should be able to get the root shell. And you can see that there. At the end of the day, that's what you want. You run exploit, it generates the bat file. You run stack, it reads the bat file. And if everything is successful, boom. Notice that because of the pound sign there, you are in fact root. Now this would assume that you change the shell to point to CSH. So at this stage of this lab, you're only there in the CSH. You completed it with CSH, not with dash. Okay. And read this about disabling things. Just read that carefully. But that, you know, once you get that prompt, you will be pretty you know, you'll feel pretty happy because you've completed things. If you want to look, now remember what I've said several times about the effective ID versus the real ID. So it should be noted that although you have obtained a prompt, your real user ID is still yourself, right? But the effective ID is now root because it was a set UID program, and you can corroborate that. I think it'll be 1,000 proceed, and then I don't know why it says 500. I don't know, it may have changed. And then effective ID is going to be 0, you know, which is root. Here's a Python version of this. You can also try that. Feel free to, you know, if you like Python, well, that's, you know, at the end of the day, that exploit file, exploit.c, could be written in any language because all you really need is the file, that file. That's all you need with the contents. So, I mean, to me, it would be great if you guys, I mean, both are great languages. So do it however you want. And then after that, I don't want to get into this yet because that just complete until this first, all right? And then, you know, phase 2 or, you know, to be continued, whatever, we will come back to this lab and finish up the rest, which is exploring, you know, dashes, countermeasures, how to get around them, defeating randomization. I think you'll find this pretty exciting, pretty interesting. I'm sure you'll like it. Stack guard. Yeah, and then it, you know, and then you can read. Certainly, this has a lot of details, so you know, you can take a read through it. Very, very interesting. All right, and that's about it for the lab. So that's what I wanted to explain about the lab today. I really don't have anything else to say. So I'm just going to pause the video. And at this time, if you have any questions, I'll stay to answer your questions. All right, guys, we're going to stop here for today. And I'll see you guys on Tuesday. So have a good weekend.
You too.